Okay. Okay, good morning, Richard. Can you hear me? Okay, thanks. Looks right at this point in time, it's just you and me right now. So I don't know, maybe some other people are either coming in later or they're going to join online. Okay, so I'm not going to go over too much of the material went through before, and we're going to try to cover the stuff that's in the depth. So we're going to go through the book and kind of skip around a little bit. Let me see where I'm going to find the right pages. Okay, what I'm planning on doing today is to go through the remaining chapters in the book, and then we'll pick up various problems that are a little bit outside these topics, but then still covered within the depth portion. And so that's kind of like a potpourri of additional problems that some of them come from the sample exam questions from NCES. So all I can do is show them to you. Can't give them to you. Then I have some additional material. And then some additional material I'll have Alex posted on the website so you can download if you want to. Okay, so first thing we're going to cover is chapter 7 of the book, and that's seepage, and we'll talk about permeability and then flow nets. Okay, are you a geotechnical or environmental? Who do you work for? Oh, okay, great. Okay, I do a few jobs down in San Diego sometimes. Okay, all right, let's do this. We got a lot of material. Since we covered a lot of material last time, I'm not sure we've got full 6 hours, but I'm sure it usually fills up to the whole time. Okay, let's do permeability. And we've got, okay, the historical background for this is Darcy's law. Darcy was a French mathematician, had nothing better to do than play with soil and water. And he was kind of interested in how water flows through soil. And he set up an apparatus where he had this, make sure I got this right, soil sample here, and he set up an apparatus where he flowed water through it, but he maintained a constant head. So, you know, he probably was out there pouring water in, and as it was dropping, trying to keep the water level constant. And then he measured the amount of flow that went through the soil after it reached a steady state. And he discovered what's now known as Darcy's law, which is expressed in this equation, where little q is the flow per unit rate of time. And he found there was a relationship where that would be equal to k times I times A, where k is a coefficient of permeability, which is unique to each soil he tested. I was the hydraulic gradient, where I is defined as the head difference divided by the length of the soil sample L, which is essentially the length of the path that the water particles have to travel through the soil sample. So that's the hydraulic gradient, delta H over L. And A is the cross-sectional area of that soil sample. So little q is equal to KIA. So that's basic Darcy's law. Now, I know this is a very hard, not very clear on this. I'll try to remember what the numbers are. Okay, this was 0. This is 10 to the minus 1, minus 2, minus 3, minus 4, minus 5. That's 10 to the minus 6. That's 10 to the minus 8. And let's see, this would be 10 to the 1, 10 to 2, 10 to the 3. This is the coefficient of permeability K, and this is in units of, I think it was centimeters per second. As you can see that there's a wide range in permeability here, you know, huge differences in numbers. And this side, says it's a good drainage. Here's poor drainage. And this stuff here is practically impervious. So obviously on the good side, you have sands and gravels. This is gravel here, this is sands. and then in this area we have clays. Okay, this is not the falling head test. What I just described is a constant head test, and then I have a problem which shows which illustrates the falling head. I'm not going to derive the equation, but just give the equation. Okay, so usually you would have problems here. You need to know the coefficient of permeability in order to solve these seepage problems. Yeah. Okay, so remember that for Darcy's apparatus, it's a constant difference in head. So it's a constant, and that equation for Darcy's law was based upon a constant head test, but the coefficient of permeability can also be determined from a falling head test. So slightly different. It has to account for the changes in head with time. Okay, so here's a possible problem where, say, if they gave you that Darcy apparatus, if they told you what the cross-sectional area A was, say it's 10 square inches, and they told you the coefficient, the flow per unit rate of time was 0.0005 cubic feet per minute, and the difference in head was 10 inches. What is the coefficient of permeability? So since we have Q is equal to KIA, then K would be equal to little q divided by I times A. So we're putting it in, then I being delta H over L. We can get in here, put in little q. Here's the delta H is 10 inch, and cross-sectional area L is the length of the sample, which is up here. So that's L. Maybe can also be should list it as 24 inches. That goes in here over L, and A, here's the cross-sectional area, converting the units. And then to get coefficient K, it's usually given in terms of feet per minute, or if you're using metric, it'd be in centimeters per second. Okay, let me move ahead. Just get some. Okay, here's a PE problem that illustrates the falling head. Okay, this problem states a local regulatory agency previously investigated using a clay liner for a sanitary landfill site, and then here they give you two test results, and you see from it, they say they test the sample of clay from a borrow site. It's determined that the minimum clay liner thickness of 1 foot would be needed. So for that particular clay that they tested from the borrow, so they get these results. If you look at the information they gave the diameter sample 2.15 inches, the height of the sample is 4 inches, duration of the test was 12 hours, and they say the inside diameter of the standpipe 0.5 inch,